Okay, the recording has started. Just to confirm, if you can still see the screen, the presentation is there with you. Just confirm to me so that we can start.
Yes,
Just
that's there.
say it, please. Because, yeah, just say it if you can see it. Okay, so it seems that you can see it. Okay, good. Okay, let's start. So, last lecture, if you remember, we stopped at direction control valves, in which we saw that okay, we have two different systems, one backup system and one the primary system of supplying the hydraulic fluid to the system. If it fails, then the second system, will take over right away automatically. So that's the benefit of this. So today we are going to start the pressure control valve, the second category of the control valves. First one we discussed about the traction control valve, and we talked about the envelopes, the ports, and the functionality and so on. Now we want to see if you want to maintain a certain pressure inside the system so that overloading is not achieved, and we avoid damaging any part of the components inside the hydraulic system. So in that case, we apply and we use these pressure control valves, the PCV. So the simplest one of those was pressure control valves. Let me just make it full screen. It should be okay. So just you can confirm just by saying that if you can see the full screen, just say it. No, don't
Yes,
type.
doctor.
Just yeah. Okay, good. Because I don't want to go back. So the whole full screen is in front of me. Okay. So let's see the construction. The construction consists of this spring. See spring, and there is a piston here. See the piston is here, and the inlet of the oil or the hydraulic fluid is here. Now, as long as the pressure inside the circuit, the hydraulic circuit, is less than the pressure setting of this spring, this piston will not go up and will not allow the oil or the hydraulic fluid to flow from here to the tank. So it means that the whole system is within the pressure limits which we want in the system. But as soon as the pressure exceeds the pressure rating of this pressure control valve, so what will happen? This piston will go up. See, piston will go up and push this the spring, and will just make this way for the hydraulic fluid to go into the tank. In this way, it will never ever be overloaded, means that the pressure will not exceed the pressure setting that we need in the system. The symbol for this type of pressure control valve is like this. So this is the main supply line of hydraulic fluid. This is the pressure control valve, in which you see this arrow is discontinuous with this line. So it means that the flow cannot go from this. Okay, and there is this line which is showing that okay, if the pressure exceeds the pressure rating of the pressure setting of this pressure control valve, then this will go up. The pressure will come here, 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 and will just move this arrow up and push the arrow up, and then this it will complete the circuit, and the flow of the hydraulic fluid would go right to the tank. In this way, the pressure would be maintained, and it will not exceed to damage any component of the hydraulic system. Discussing about this plot, we have a pressure on the y-axis and we have the flow rate on the x-axis. So what happens as long as it is closed? So this plot is for this pressure control valve. As long as it is closed, it is below the pressure rating or the pressure setting of this pressure control valve. So there will be no flow. The pressure will keep on increasing, but there will no flow because we will not let the fluid to go into the tank. So there will be no flow. But as soon as this point comes, it's called cracking pressure. The cracking pressure is the pressure which is the pressure setting of the pressure control valve. At this point, the piston is pushed forward and pushed upward, and then the start of the flow would begin. But gradually it will be less at the beginning, and then as the pressure exceeds further, it just continue to increase the flow. But you can see after that the pressure increase is very slight, very gentle, whereas the flow rate is more than the increase in the pressure until you have the pressure control valve fully open, and you will have the maximum flow flowing through this pressure control valve. So the pressure at full pump flow. So it means that it will allow the entire pump flow passing through this pressure control valve. Okay, and then the flow will be at, of course, maximum, which is in the cubic meter per second. Okay, going to the next, it's a partial hydraulic circuit. So this is what we have schematic of this partial hydraulic circuit, in which we have this tank, the reservoir, the filter to just to let no foreign object or no foreign particle to flow with the oil, and then goes to pump at high pressure. It will go to the system, see to hydraulic system. So if it is a hydraulic cylinder or hydraulic motor, whatever the work is to be done, is done here. But of course, there will be a constant check on the total pressure in the entire hydraulic system. We don't want the pressure to exceed so that it can damage anything here or here, anywhere. So it means that we are going to just take one line and attach this install this pressure control valve, and the same mechanism would be there. So this spring is showing this spring, which is set manually with the help of a knob to set the required or desired pressure setting in this pressure control valve. The second one is the compound pressure relief valve. This is also a pressure relief valve, which is of course to control the pressure. So if you want to release the pressure, so there is this is the actual photo of this compound pressure relief valve. This type of pressure relief valve is used if someone wants to use it in the hydraulic circuit remotely and remotely control it, or do the setting so that you don't have to go closer to it. So in that case, you use this type of compound pressure relief valve. So how it works? So for this, you have to see the cutaway diagram of this. So you see, this one is the piston of the pocket, which would not allow the flow to go from here to here. Okay, so it is going just straight. Okay, now this is connected with the tank. So as long as the pressure setting is below the pressure setting of this whole system, so the oil will go normally from here and it will pass through it and it will go here. Okay, so what is this? This is the hand knob that can control the pressure setting. Okay, so there is a poppet here, small poppet here, which you can see here. It's a conical poppet which is closing this opening to this drain valve. You can see here it's continuously, but it's not there. If you just see that here, so you see here it is closed. So it means that if it is closed, it will not let any oil to go through this drain valve. Okay, so as long as it is closed, the oil will come here, and at high pressure, of course, from the pump, go through this small orifice. Small orifice go up, and there will be same pressure here as well as here. So in that case, it will not allow, because since the pressure is same on both sides, this piston, which is sitting on this on this opening, will not go up because the pressure is same. So it will be just resting and sitting like this. But as soon as the pressure exceeds, and also the oil comes here until here, okay, it will not go here. It will just rest here and it keeps on pushing this one. But until the pressure setting of this is exceeded by the pressure of this oil, it will just push this pocket backwards, and that would allow the oil to go through this drain valve. As soon as the oil goes through this drain valve, the pressure on this side would drop because the oil will go out. So the pressure will drop and it will just push this piston upward. As soon as it goes upward, so the opening will be available and the oil will go, instead of going in the forward direction or forward, just go through this into the tank. Why into the tank? Because the tank is at atmospheric pressure, whereas the hydraulic motor oil cylinder is at a certain higher pressure because the work has to be done. The oil will just be drained to the tank. So this is the compound pressure relief valve. This is the figure of the actual picture of the compound pressure relief valve. Two-way built-in solenoid activated. So it means the solenoid is there to activate instead of this hand twisted. The solenoid will define, of course, the direction, the pocket setting, and so on. So vented when solenoid de-energized. So as soon as the solenoid de-energizes, so the drain valve would open and it will let the oil go, and that would allow the main oil flow to go to the tank. be vented when the solenoid is energized, means that if it's powered by electricity, it will keep the poppet closed. The maximum flow capacity is 53 gallons per minute and limit system pressures up to 5,000 psi. The next is a pressure reducing valve. This type of valve is used in the hydraulic circuit if we want to maintain a low pressure at certain section of the hydraulic system. So how it works and how is the construction, you see there is also again a hand knob that you can set the pressure setting. This is a spool which is bleeded. Bleed means there is a small thin slot in between. Okay, this is the inlet of the oil and the outlet of the oil. So as I mentioned, to reduce pressure system. So it means if you want to maintain a reduced pressure system, we use this type of pressure reducing valve. So this is bleed oil passage, and this is the spring holds that valve open. Now what happens? The inlet goes in, goes here, and then it goes out. But at the same time, there is a branch of this outlet hydraulic fluid going and pushing this spool from this end. Okay. As soon as the pressure increases at the downstream end, which is the outlet, it will just push this spool to the other side. As soon as it exceeds the pressure setting that we did or the operator did, so it will just push this and move this towards the right. As soon as it moves towards the right, you see this spool land will close this. See, it becomes smaller. So when it becomes smaller, so as soon as the opening becomes smaller, the flow rate goes down, and at the same time the pressure goes down, and then it will maintain the pressure that is required based on the pressure setting by this knob in this spring. But what happens if this continues? This high pressure can push it further until what happens. It is possible that this opening of the outlet is completely closed by this land of the spool. So in that case, it stops. The pressure drops here, but this oil, which is already here, it will be it will be at high pressure because it is already pushing this spool. So this high pressure oil would come again here because this is leakage here. You can just go through this one reverse direction and to again generate and maintain a high pressure, which is not desired. So in order to make sure that the high pressure is not achieved here and it's not again developed here, so we there is this bleed. You see here this one. It's a very thin slot through which the oil keeps on going, and it will go to the drain means it will go to the reservoir. In this way, the high pressure oil is not established here, but the oil keeps on going, and a moderate pressure is developed with a partial opening so that the pressure is well maintained and the required pressure at the outlet is achieved. And the symbol for that is like this. So this is the flow. Then see, in usual practice, it is closed, it is open. Before, in that case, it was for the pressure relief valve, it was closed, right? When the pressure exceeds the spring settings or the pressure settings in the pressure control valve or the pressure relief valve, then it opens and the circuit is established. But here in this case, you see that it is already open or the circuit is open and the oil and the hydraulic fluid is going from inlet to outlet. Okay, so as soon as the pressure exceeds the pressure settings of this spring, it will just go up. When it goes up, it will just reduce the opening, as you can see. In that case, the this small bleed, which is a small slot in between the spool, would drain the oil to the tank, and this is the spring that is shown. Now this is another one which is called unloading valve. This type of valve we use if we want to unload whenever there is requirement to unload the entire hydraulic system to the reservoir or tank at atmospheric pressure or at zero gauge pressure. In that case, this type of unloading valve is used. So the inlet is A, and this is B, which is going to the tank or the reservoir. So as soon as it comes here, so this is the piston which stops the way and it stays there. But some portion or some small portion of the oil would go through this, goes up and tries to push this one here. But there is again a pressure setting of the spring controlled by this knob. So it means it will not allow, the spring will not allow this oil at certain pressure to push this and make this opening open, or make this port open for this hydraulic oil. In that case, just stay here. As soon as the pressure exceeds the pressure setting of this spring, the high pressure oil which is going through this, it will push this and it will go further until you see that the passage for this port will open. This port is again a drain port will go back to the reservoir. So as soon as it goes, the pressure and at this level, at this stage, at this section of this, the top section of this valve would, would drop because the flow is now going and the pressure would drop. In that case, what will happen? There will be a pressure differential between this lower side of the piston and the upper side of the piston. It will, this high pressure oil will push this one because now the pressure is lower on the top side, on the upper side of piston, and will push this one and this opening will open and the mainstream hydraulic fluid will go to the tank. But this is the arrangement in such a way that the opening of this drain will be at zero gauge pressure or atmospheric pressure. This is the actual picture of the unloading valve, and this is the schematic or the symbol of this unloading valve, which is the main line. This is the line which is shown here. Okay, as soon as this becomes high, it will just open this, or this port. All this arrangement will go forward, and then this piston will be pushed forward, and then the circuit will be complete. The whole supply of hydraulic oil, hydraulic fluid will be drained to the tank at atmospheric pressure or zero gauge pressure. The other one is the sequence valve, which is the valve which we, if you remember when we discussed the sequencing of the welding process, this type of sequence valve, because at that time we didn't talk about what type of sequence valve it is, but this is a sequence valve which has a pressure setting. So this is the sequence valve. This sequence valve would allow the oil to go partially through this opening when the pressure setting of this is reached. So it means now what happens? The oil comes here, it goes through this, and it reaches here and tries to push. But again, it will not go because the pressure setting is established by this knob, and this spring will not allow the oil to push this whole setup in the forward direction. As soon as the pressure setting are exceeded and the hydraulic fluid, so it will push this one, and there will be a partial opening from this. See this triangular thing, this triangular pocket. This pocket will go backward, and there will be a partial opening here, and the oil will go through the this drain port to the tank. In that way, the top pressure or the upper pressure on the upper section of this piston will decrease. It will push it forward, push it upward, and then this oil will be drained to the to port B. And it's drained to port B, uh, which will allow a partial flow of the hydraulic fluid from port A to port B. So now in this whole scenario, if we want the oil to be sent to port B, to the tank, we can just connect this one to the tank. If we want it to go to the other side of the hydraulic cylinder or hydraulic motor, we do the same. The symbol is this one, and this is the main line, and this is the line which you can see from here. Again, it is not connected, it is disconnected. The oil cannot flow through it because the piston is restricting the passage. This is the spring, which is this one, the pressure setting, and this is the tank, or we can just use it for other purpose. But in this scenario, we just put this into the tank. This line, which is the dash line, is this one. Okay, please pay attention. This line is C solid. Okay, this line is solid because this will go, of course, but the main supply is this one, which will drain and discharge the entire hydraulic fluid supply to the tank at atmospheric pressure. But here you have two supplies. One is this one, which goes to the tank, and also this one, which will be the partial supply moving from port A to port B into the tank, or if you want to move it to some other point in the circuit, you can do it. Just a minute. Give me a minute. Going further, The other pressure control valve is a counterbalance valve. This is a very interesting valve because this valve would allow you to raise or lower the load gradually or slowly. Okay, how it works? Let's see if you want to move the load downwards gradually and slowly using this counterbalance valve. This whole setup is done like this. So let's see the parts and try to understand. Number one, this is the directional control valve. Number one. Okay, so this will allow the direction of the hydraulic fluid to go going to the desired direction. They want to move it. This is the cylinder in which you have a piston, and the other side of the piston, there is rod, and the rod is filled with the load. Of course, load needs to be lowered gradually and slowly. Okay, this is the directional control, this counterbalance valve, which is having again a pressure setting, and a spool is there, which is actually uh, closing this port by the land, with the help of the land of this spool. So what happens? If you want to lower this load slowly, we are going to put the direction of the direction control valve in such a way that oil, of course, we want the oil to come here, okay, to come here. But you see, from the pump, it will come from here. So just we follow the direction of the hydraulic oil. The oil comes from here, okay, then goes here, okay, and then it goes to the cylinder, okay. But we want the cylinder to go gradually, so it means that resistance must be provided at this point, so it goes down slowly. Otherwise, if there is no resistance here, it will just drop suddenly. So it means there should be a resistance. Now let's follow. The oil is going because now it is pushed because the oil is coming from the pump at high pressure at the blank end of the piston of the hydraulic cylinder. The rod end of the oil at the rod end would go through this passage, through this passage, through this passage. It will come here. Okay, it will come here. When it comes here, there are two things. Number one is this check valve. This check valve is closed. This check valve can be used to have the flow from the top to bottom, not from the bottom to top. So it will just close. Okay, oil cannot go from here. Then it will come here and we will stop because the land is closing this, and then it goes here. See here, it goes here, it comes here. When it comes here, it tries to push it upward. Now this whole spool is connected with the spring, and the spring is again adjusted with the required pressure settings. So as soon as the oil, because now the oil is coming from the pump, it is pressurizing. So the pressure also is developing here. But again, in doing so, since there is no flow through this, it will be stopped until the desired pressure is achieved. And this oil, which is branched here, will push this spool upward. When the spool is pushed upward from this branch of this high pressure oil, the spool will go up and the land would make the passage very small passage, a gradual passage that would allow the oil to go, in small quantities to the tank. So since the flow is, uh, partial, so it means that it will not let the load or the weight to go very quickly downward, but it will go very slowly because it will depend on the flow rate of this incompressible hydraulic fluid to go from this end of this port to the tank. So that's how you will allow or you will achieve the slow descent of the load. Now, if you want to do it the other way around, you want to move the load upward, okay? So you can just do the same, just change the direction of the direction control valve, okay? In such a way that instead of now the oil coming from the pump to the blank end of the hydraulic cylinder, it goes to the rod end of the hydraulic cylinder because now you want to make it move up. So in that case, the pump hydraulic fluid would go through the direction control valve. Now it will go through this passage. But now since it comes here, you'll see that the land of this pool would close the passage. So it cannot go from here and come here. So it will again find a passage or an opening through which it can go through this passage to the rod side of the hydraulic cylinder. In that case, it will just push this check valve downward. As I mentioned, that it can allow the flow to go from top to bottom, but not from bottom to top. So you push this check valve and it will freely move from here and then through this to the rod end side, and then it will just push it upward. So that's how it goes. And again, This oil, which is here on at the blank end of the hydraulic cylinder, will go to the tank. So that's how this counterbalance valve can be used to lower the load slowly, and also even to let the flow in such a way that the load is raised slowly as well, because this will allow the flow, but it will have a restriction for the oil to flow at the right rod end of the hydraulic cylinder. The symbol used for this is like this. See here, this is the check valve that I was talking about. This is the spring setting is here. This is the main line. You can take this main line. Okay, now it is closed. Right now it's closed. But now this line is pushing it. This line is pushing it upward. Okay, as soon as the pressure setting is achieved and it's exceeded, we will push it upward. So this arrow will be pushed upward to make the circuit complete, and the oil will flow from this line to the line where you want to move the oil. Okay, in this way you can just use this one as the symbol to use. Now you can see here, this one is the dash line which is coming from the auxiliary port to back into the main supply. Okay, the third category is the flow control valves, and these flow control valves are the valves which are used to control the flow rate of the hydraulic fluid. And we know that controlling the flow rate of the hydraulic oil would control the extending speed and the retracting speeds, or the extending velocities, or the descending and the uh, uh, retracting velocities of the hydraulic cylinder, or the RPM of the hydraulic motor. So it means controlling the flow rate would control the speeds and the amount, the nature of the work that you can control with the help of this flow rate. So the easiest one or the simplest construction of the flow control valve is the orifice meter, or the orifice. The orifice is a disc, a circular disc with an opening in the center, placed in the channel on the pipe where the flow of the hydraulic fluid is going on. So orifice as a flow meter or a flow control device. Okay, flow meter means that if you want to measure the flow rate, you can just use two gauges P1 and P2 and take the difference, and you have the formula. You just put the formula to find the flow rate of this hydraulic fluid. You can find very easily, and also you can control. How you can control? It's very easy. If you increase or decrease the opening of this orifice, the flow rate can be controlled at a given pressure. Okay, and if you want to if a given flow rate, if you want to get the pressure differential, have more pressure drop, you can have it also very easily. There are two different types of orifice. One is the sharp edge and the other one is the square edge. Okay, both have their own purposes and functions. Now to find the flow rate, this is the formula. This is the formula for that. This number is actually a constant number which is used for these types of orifices. C is the flow coefficient, okay, and it is 0.8 for sharp edge and 0.6 for square edge. So C is the one that will make the difference uh, between these two different types of orifices. A is the, of course, the area of opening. So area of the orifice opening. Delta P is the pressure differential, the pressure gradient, which is across the orifice. It's mentioned that pressure drop across the orifice, which is P1 minus P2. P1 is higher, of course, and P2 is lower because the flow is from left to right, and as is the specific gravity. So it means if I give you a problem in which any of the parameters to be calculated, so you just put in the formula, substitute all the values and find the unknown parameter. Now, continue with the flow control valves. The first one, which is having a construction, is called the needle valve, which is the very simple of the flow control valves. This is something like a tap, and the tap also something similar is there. There is the water supply, and there is this uh, triangular pocket that closes the opening, and when you just turn it, you just go up and let the water flow. And of course, the opening would define the flow rate which you desire. So use to regulate the speed of the hydraulic cylinders, because if you increase or decrease the flow rate, you are going to increase or decrease the speeds of the hydraulic cylinder and hydraulic motor. And those are these. actuators. So needle valves are used to give fine control because you can just finally open and close and control the opening to control the speed of the actuators. So this is the schematic and this is the actual picture and the actual photo of this needle valve in which you have these numbers to show that okay how much you have opened. So as a reference, and there is a spindle in the middle which has different colors. It's actually made of different colors. So it means if you have a particular number that will come up, it will show you how much needle valve is open. And if you want to have it locked at this particular location, as with this particular opening, you can just use this, turn it, it will be locked. So then you cannot turn it. In that case, constant supply of flow rate at desired value can be achieved. The formula to find the flow rate for this type of needle valve is CV delta P over Sg. CV is the capacity coefficient, which is which is as a unit of liters per minute per square root of kilopascal. So for this particular type of formula, we will not convert the Q into meter cube per second, but we'll keep Q as liters per minute because the unit of CV is liters per minute over square root of kilopascal. Okay, so it means that delta Q can also be kept as kilopascal. Sg is the specific gravity of that. C is measured kilopascal, and Q is in liters per minute. So capacity coefficient, what is capacity coefficient? Defined as the flow rate of water in liters per minute that will flow through the valve at a pressure drop of 1 kilopascal. So it means if you have a pressure drop of 1 kilopascal across the needle valve, the flow rate would be equal to 1, which is the capacity coefficient. Okay. Of course, it will be 1 this liter per minute per square root of kilopascal. So CV is determined experimentally. So this capacity coefficient is determined experimentally with the different methods in the fully open position, and it is listed as the rated CV in the manufacturer's catalog. So it means that you open the needle valve completely and then do the experiment to find its value. Once it's determined, the manufacturer will provide the CV value to the one who is going to purchase it. The next one is the flow control valve, which is called non-pressure compensated valves. These are used where you have, relatively constant pressures, and the motoring speed means that the actuator speeds are not too critical. Okay, so such type of situations we can use this type of non-pressure compensated valves. Now the inlet is from here. Inlet is from here. So the free flow in this direction. So it's free flow in this direction. It comes here. Okay, it comes here, it goes. Now what is this? You can adjust this screw so that you can let the required amount of flow through this. Now there is a check valve. Okay, so from here when it comes, it will push this down because the springs here. It's a very light spring that can be pushed very easily by the hydraulic fluid. It will push it and it will go right like this. But if it goes from here, it will not be able to push it. See here? So this direction, the flow is controlled, but from this direction, the flow is free because it will just push this one through the spring over here and it will go freely from this end to this end. So this check valve is not allowing it to go in the opposite direction. Okay, so in that case, the symbol shown is like this. See here? So like this, from here it can go freely, the pointed end of the control valve, and then it goes like this. Okay, but this one, why did we make it this one? Because it will define, or it will be, will be defined when it pushes it. So the required amount of opening will be provided based on the setting of the screw and the spring, which is desired. So it means if it pushes, it will push to the desired stiffness of the spring that will allow the required controlled flow rate through this freely. The flow through the orifice will be constant if the pressure drop remains constant. So this section, which is called as orifice, will be constant if the pressure drop across this remains constant. Now the other one is a pressure compensated valves in which you have the pressure fluctuations, and you want the flow to be to control the flow, and you have a desired flow for a fluctuating pressure inside the whole entire pressure. entire hydraulic circuit. Okay, so let's read this one. See this whole equipment and all the components. This is the spring. The spring load sets pressure difference across the throttle. Okay, we will define the pressure. This area equals combined area of annulus and stem. So this is the area, the combined area of the annulus, which is this annulus region, and the stem, which is the stem. So hydrostat piston is this is a hydrostat piston and is balanced between intermediate pressure below and load pressure above. So load pressure is from the spring and then the hydro pressure is from the bottom uh, from pump. So the oil is coming, or the hydro fluid is coming from this, from the pump. Land blocks. So this land blocks excess flow and forces it over relief valve. Okay, so what it happens, this is the stem. Okay, so this land blocks this and forces it over the relief valve. So the relief valve is from here, and from here, not from here. So this is blocked, and this is a gradual small opening from here. Okay, then the throttle control. This is a throttle here that would allow the required amount of flow to pass through this, whatever the fluctuation is. So it means it will control the fluctuation if there is, based on this fluctuation coming from the pump or some other factors. It will allow the required amount of flow from this throttle. Okay, so the oil will come, it will just be pushed, of course, pushed here. But again, since the pressure setting is not achieved or not reached, so it will just allow it to remain there. It will just allow this flow to go through the throttle and to the load or to the hydraulic cylinder. The symbol for that is, you see here, it comes here, this needle valve, because this throttle is actually controlling the flow rate. Okay, and then this is the one that will allow it to increase. Now from this one it will not lose. You see it is not allowing it to go through this. It's closed. Okay, but if it goes to the other, from the other side, it will just push and it will just go to the other side. But anyway, the usual direction of the hydraulic fluid is from left towards right. This is the actual part of this pressure compensated valve, which is actually a model which will show the entire construction of this valve. And the pressure compensated valve, pressure rating of 3000 psi, it maintains a preset flow within 1 to 5% of the basic flow rate, and flow rate capacity can obtained within 270 degrees R. Now, by just turning this one, you can control the throttle setting. Okay, just this one. This is the benefit of this. Just by turning it, you can control the amount of flow and as well as the throttle opening by this turning of this dial. Now, the one that is here is called proportional control valve, also called electrohydraulic proportional valve, and it's electrically controlled, used in open loop systems. Okay, open loop systems in which the oil or the fluid would just pass and will go into the surrounding, or it will be just open. It will not be a closed loop. Uses a solenoid that produces a force proportional to the current in its coils. Okay, by controlling the current in the solenoid, the position of the spring loaded spool can be controlled. It has both directional and flow control capabilities. Now, what it means? It means that this type of proportional control valve uh, would allow an infinite, infinite settings or infinite positions of the spool, so that you can control very precisely the flow rate that you want from this type of proportional control valve. So the direction means that since it is a spool, so it means if you just move it completely, it will change its direction. And if you apply electricity or current to the proportions where it just moves gradually or partially, then you can control the flow control or the flow rate of the hydraulic fluid. So that's why this is a very handy and very useful valve that can serve as a direction control valve if you apply the current completely so that the spool would open and close the ports completely, or you can just control the spool movement proportional to the amount of current provided to the solenoid. Okay, the solenoid would again the same thing. So that's why you see this one, because in this case you will be able to control the spool position based on the partial application of the electric current, and that would allow the spool to move gradually. These two lines, which are additional to horizontal lines, are drawn because these lines represent that infinite position of the spool, or infinite possibilities of flow rate can be achieved by applying the partial current to the solenoids. And the spring, of course, spring centered, because you want, if there is no current, it should come out with be in the middle, the neutral envelope of the position, which is shown like this. So it means that A and B will be connected with the tank, so that if they need to discharge the oil and unload the oil in the tank, they can do it very easily when there is no operation going on and the pump is stopped. Okay, and then of course the application of the solenoid would allow it to move gradually in both directions to control the flow rate, as well as to control the direction of the hydraulic oil. Two horizontal lines representing, we mentioned, intimate spool positions. Clearance between the spool lands and mating valve bore is approximately 0.0005 inch, which is very, very small opening or small recess between the land and the casing uh, of the valve. Maximum flow rates of 7.9 grams per minute, pressure drop of 125 psi, supply voltage of 24 volts DC is supplied. So this is the simple for the proportional control valve, and this is the actual picture of the valve. This is the schematic, and this is the cutaway view of this entire uh, proportional control valve. Now, we finished with all the valves, in which we discuss about three main categories of the valves. Number one is the direction control valve, in which the only purpose of the valve is to control the direction from the pump to the blank side of the hydraulic cylinder, or the rod side of the hydraulic cylinder, or changing the direction of the hydraulic motor. Okay, and the second category was the pressure control valve, in which you control the pressure inside the hydraulic circuit, either at a reduced value, or you want to protect the components so that you can do the setting such a way that as soon as, because of the because of a very resistive load, the pressure will not exceed the desired pressure rating of inside the entire hydraulic circuit, so that nothing is damaged inside the whole circuit. The third one is the flow control valve, in which you can control the flow of the volumetric flow of the hydraulic fluid, so that you can have the desired velocities of hydraulic cylinder as well as the hydraulic motor. So we discuss all these different types of the valves and their functions. Now we're going to see some problems. I have already put the solution of all those problems that we are going to discuss now very quickly, and I'm going to show you and explain you all these uh, procedures and steps, so that you understand and you can do yourself for the practice as well as for the preparation of the exams. So let's see this example. This example is the first example in the book. Let's read it and try to understand, and then we are going to solve. Even though the solution is very simple and very short, but it will give you a very good insight about how you're going to use simple formulas to find some different parameters inside the hydraulic circuit using the valves. So it means this is all related to the valves, how we are going to calculate different parameters in the valves. A pressure relief valve. Okay, so this second category contains a pocket with a 0.75 inch square area on which system pressure acts. Okay, this is the Gaussian area on which the system pressure acts. During assembly, a spring with a spring constant, so K value is given, is installed to hold the pocket against its seat. The adjustment mechanism is then set so that the string is initially compressed 0.2. So the initial compression is 0.2 inch. By the way, this all the examples are in English units, but again, I included intentionally so that we at least get to know the entire procedure and all the steps of the solution. So it means if I give you the problem something similar, everything would be just in the same. So the procedure, the formula exactly would be the same. So it's initially compressed 0.2 inch from its free length condition in order to pass full pump flow. Okay, in order to pass full pump flow through the valve at the pressure relief valve pressure setting. So it means I'm looking for the maximum pump flow. So it means it will be at the end, not the cracking pressure, but at the full pump flow pressure. The pocket must move 0.1 inch further so that the full pump flow conditions can be achieved. From its fully closed position, determine on the number one the cracking pressure, the pressure at which the pressure setting by the hydraulic fluid is achieved, and number two, the full pump flow in which the pressure relief valve will be opened completely. Okay, let's see. So the pressure relief valve. Okay, so area is given 0.75 on which the pressure is applied. The K value, the spring stiffness is given. Uh, the compression, which is S, is 0.2 already. Okay, already done. For full flow, the compression is further 0.1, so it means total 0.3 inch would be this spring would be compressed 0.3 inch completely in total if we want the full pump flow through the pressure relief valve. So we want to find the cracking pressure and then the full pump flow pressure. So solution for part A, when we want the cracking pressure to be obtained and to found. So we know that the force a spring exerts would be equal to spring constant into spring deflection. We know that Ks, we know that. So we want to find the spring force. So spring constant is the stiffness of the spring, and S is the deflection already done as equal to 0.2 inch. So when you multiply, you get a force of 500 pound force, which is applied by the spring. Now we know that if we want to find the cracking pressure, so that cracking that force which is applied by the hydraulic fluid should be equal to the force which is applied by the spring. When these two forces become equal, so this hydraulic force will be able to start opening to start pushing the spring and start opening the port to the tank. So it means we can equate those hydraulic force is equal to spring force. Hydraulic force is equal to, of course, we know the pressure into area, and spring force we just found. Now we know this the area over which the pressure is applied. We divide by A, which is 0.75, and we get the cracking pressure. That's it done. We have found the cracking pressure. Now for the full pump pressure, so when the spring moves further 0.1 inch further, the total compression is 0.3, right? So 0.2 already, and then 0.1 further to make it full open. So the spring force exerted on the poppet when it is open is, of course, K into S again. Now this time is 0.3, right? Before it was 500 pounds, but now, since it is fully open and the spring is further compressed, it will be 750 pounds of force that is applied by the spring on the pocket. Now, again, we equate the hydraulic force because this hydraulic force will be able to push this so that in the full opening of the port of the pressure relief valve is achieved. So, hydraulic force equal to spring force, hydraulic force equal to pressure, which is full pump flow into area is equal to 750. Area for the same, divide, you will get 1000 psi, which is the full pump flow pressure, which is obtained or which is achieved at the pressure relief valve to open it completely for the full pump flow. Now the second example, a pressure relief valve has a pressure setting of this. Okay, so pressure setting is given. Compute the horsepower loss across is this valve if it returns all the flow back to the tank from a 20 gallons per minute pump. So we have been given the volume flow rate and also the pressure setting. So it means we are given the pressure setting P, we want to find the horsepower, which is the power, and we are given the volume flow rate, which is 20 gallons per minute. So it's very simple. We know that the formula for horsepower is P into Q. If you are dealing with SI units, then this 174 will not be there. We just be P and Q, P in kilopascal in Pascal and Q in meter cube per second, and then you'll get the power in watt. Okay, but since it is horsepower, you're going to divide by 174. But again, as I mentioned, The only thing which is different is that I'm not going to give you any problem related to English. So it means you just have to worry about or to care about the power equal to P into Q, the hydraulic power. So that would be enough. But anyways, for this problem, you just divide by 171 for P is given, Q is given, just put the values, you get the horsepower as 11.67 horsepower. Next problem, which is an example, an unloading valve is used to unload the pump of example 8-2. Okay. If the pump discharge pressure during unloading equals 25 psi, so the discharge pressure is given, how much hydraulic horsepower is being wasted. So if we have the hydraulic pressure instead of 1000 is 25, how much hydraulic horsepower is wasted. So instead of now 1000 is just 25. Okay, and Q is the same. So again, we will find the horsepower is 25 20 over 1714. It will be 0.292 horsepower as compared to this one, which is 11 horsepower. This was would be this one is 0 0.2, which is very small as compared to that one. If we reduce the discharge pressure from 1000 to 25 psi. Now let's go further. Next example, a flow control valve. No, we are talking about flow. So far we were discussing about the pressure relief valve. Okay. Now we are going to talk about the flow control valve. Experience direction. But for direction control valve, we don't have much numerical problem because they are just changing the direction, nothing else. But the pressure relief valve is, is changing the pressure, and the flow control valve is changing the flow, the volume flow rate. So that's why these two types of valves involve much of the calculation of the numerical problems. So flow control valve experiences a pressure drop of 100 psi. Okay, so 100 psi is the pressure drop across the flow control valve. Okay, which is of course equal to 687 kilopascals. So they have given the SI units for that. For a flow rate of 94.8 liters per minute, again SI units. The fluid is hydraulic oil. Okay, fluid is hydraulic oil with a specific gravity of 0 0.9. Determine the capacity coefficient means CV. So in that case, we don't have to convert this into meter cube per second. Number one, we don't have to convert into Pascal. We have to keep those because the capacity coefficient has the units of liters per minute per square root of kilopascal. Here we go. So pressure drop is of course P2 minus P1 or P1 minus P2. It is 100 psi, which is equal to 687 kilopascal. Q is given as 94.8 liters per minute. Specific gravity is given. Capacity coefficient. The formula, of course, is this one. Q is given, delta P is given, and SG is given, which is specific gravity. Put the values, you get the result in liters per minute over kilopascal square root. But here, very important thing is the units. Even though I always stress you guys to make in the base SI units, but in this, especially for this problem where the capacity coefficient is calculated, the unit of this capacity coefficient requires that we don't change the liters per minute to any other unit or kilopascal to any other unit. Now let's see this one. This is a interesting problem. It's an example, but this will give you a very good idea of this whole circuit, how you calculate different parameters using this circuit. So let's try to understand first the circuit. So this is the pump, which is taking the oil from the reservoir or the tank, and with the pressure QP. This is your pressure reliever, PRV pressure reliever is there. So if the pressure of the circuit exceeds the desired pressure in the circuit, it will open and will just drain all the oil to the tank. It goes here, the Q cylinder, the flow rate that goes into the cylinder with the pressure of course P1, and then it pushes it. At the same time, this oil, which is on the at the rod side of the hydraulic cylinder, will go at certain pressure with a needle control valve. That needle control valve of this needle control valve is controlling the flow rate out of this rod side of the horizon. Okay, so if you just reduce it, so the direction of the sorry the velocity of the extending velocity will decrease. If you open it, the extending velocity will increase, and it is getting the pressure, which is of course at the atmospheric pressure, what's going into the tank at atmospheric pressure. So this is the whole scenario. So we have three pressure gauges. One pressure gauge is at the entrance of the blank end of the hydraulic cylinder. Second one is at the rod end side, exit of the rod side of the hydraulic cylinder, and the third one is the one that is just before the hydraulic tank. So a needle valve is used to control the extending speed of the hydraulic cylinder. So if you reduce it, the flow rate will decrease, and then the velocity or the speed of the extension of the piston will decrease. The needle valve is placed in the outlet. Okay, it's placed here, outlet line of the horizon as shown in the figure. You can see that. The following data are given. Number one, desired cylinder speed. So cylinder speed is given as 10 inch per second. Again, it will be just a matter of units, but we see the procedure. Cylinder piston, the diameter is 2 inch. So this is 2-inch diameter. Center rod diameter is 1 inch, as mentioned, and of course these are the areas of cross section given for the piston and rod respectively. So cause a cylinder load is this is a load which is of course being moved by this whole system. Specific gravity of oil is given. Pressure relief valve setting is given as 500 psi. So it means that P1 should be 500 psi. Determine the required capacity coefficients in CV of the nuclear valve. Look here. D piston, D rod, area rod, everything is given. Pressure, as I mentioned, P1 is the pressure relief valve 500 psi. Specific gravity 0.9 L cylinder, which is um, uh, the uh, the force, this one, upon force, which is the force due to move. Now, here this one is important because now we want to find again the net cross area, which will be allowing the oil to flow at the rod side of the rod center. So it means we have to have the difference of the area of the piston minus area of the rod. We do it because since we have the area, we just subtract and we get the area at the rod end side, the rod side of the hydraulic cylinder. Once done, we need to find CV. Force balance on the hydraulic cylinder. Now let's see the force balance. Force balance is like the second law of motion, which is second law of Newton's second law of motion, which is summation F, the sum of forces equal to ma. Now, MA here is mentioned something like that. Maybe it's mentioned here. It's extending speed to control the extending speed of the cylinder. Okay, here it's not mentioned clearly, but from the statement it seems that the velocity is constant. Okay, desired cylinder speed. So it means the velocity is constant. So it means there will be no acceleration. Now let's see how many forces are there. Number one, first force is this P1 into A1, which is the area of the piston. This is positive because it is going from left towards right. Then there is a force which is opposing this, which is in the opposite direction. It's minus P2 into A2. Minus P2 into, and A2 is the difference, of course, between A1 and A0. And then the next is, of course, F load. It's also opposing this force, which is, of course, F load, which is just like F load is equal to M load. Now, constant velocity, which is 10 inch per second, so it means acceleration is 0. So ma, this will go away. So you'll be left with 1, 2, and 3 terms. One for the force at the blank end, another force at the rod end, and the third is the load which needs to be moved or pulled. So that makes it very easy. So we have P1 with us, we have A1 with us, we have A2 with us, we have F with us, we can find P2 very easily. Here. So we put P2 on one side and then we put the values and we get P2. Okay, P2 is the pressure at the rod end where the oil goes out of the hydraulic cylinder. Once the P2 is calculated, I can find the Q from here because for the capacity coefficient we need Q. Okay, so Q is equal to A2. Now why A2? Because I need to have the flow rate of this end, and this end is A2, which is A1 minus A rod. So I put A2 into V cylinder, which is the cylinder velocity, which is desired as 10. You will find the volume flow rate as 3.5 inch cube per second. So again, I'm going to convert into the gas per minute because the capacity coefficient formula requires the volume flow rate to be gas per minute because the unit of CV in English units is gallons per minute per PSI. So we convert it into, of course, you don't have to do it because I'm going to give you all the data in SI units, so you don't have to worry about this. Yeah, but you should know if I want to convert the volume flow rate from liters per minute to meter cube per second, this you should know. I will not give the convenient for such type of a simple conversion. Now P3 is equal to 0. As I mentioned that the P3 is 0 because it is the pressure which is going to the reservoir or the tank which is at atmospheric pressure. So it means the gauge pressure is 0. So that's why P3 is 0. Because P3 is 0, so it means P2 will be equal to delta P. And delta P will be of course P2. That P2 is so P3. So P3 is 0, so it goes away, it's minus P2. Okay, the delta P will be equal to, of course, P2, which we just found to 42.56 psi. This is the value. Now, why minus? Because it is discharging, it is, this P3 is 0 and P2 has some value. But anyway, we are going to just take this value as positive because we cannot take this. If we put this delta P as minus, it will come out to be imaginary or complex number. But anyway, this is one thing. But the other thing which was mentioned at the beginning, that in that case, when you have to find the volume flow rate using the orifice or some other devices like flow control valves, in that case, you will take instead of P2 minus P1, you will take P1 minus P2 because you know always P2 is at low pressure and P1 is at high pressure, and providing the pressure gradient would allow the flow to go from left to right. So that's why we just take 242 as positive. We put it here. 6.1 Q we just found here, which is here, gallons per minute. Put gallons per minute here, 242, which is in PSI as I mentioned, over specific gravity, which is 0.9, you get 0.372 gallons per minute over PSI square root. That's how you find the CV. But the important thing here in this, that for the whole circuit, you will find the sum of forces correctly. Let's see this one. This problem is 8-46 and it is linked to 8-45. So we're going to talk about both. So what should be the initial compression of the spring in pressure control valve in exercise 8-45? So that's why I put this statement. If the full pump flow pressure is to be 40% greater than the cracking pressure. So it means the full pump flow should be equal to 1.4 times the cracking pressure. Okay, so this is the relation that is given to us. So we get the rest of the data from this problem, which is 8-45. A pressure relief valve contains a pocket with 4.2 centimeter square area. Now C is in SI units, on which the pressure acts during assembly. A spring with a spring constant of 3200 newton per centimeter is installed. So K value is given in the valve to hold the pocket against the seat. The adjustment mechanism is then set so that the spring is initially compressed 0.5. Now, here you need to see that the initial compression is 0.5 centimeter forwards, but you need to find the what should be. So it means that this initial compression is not there for this. This for this particular problem. We are not going to take this one, but we are going to find this initial compression based on these data values. On this free length condition, in order to pass full pump flow through the valve and the pressure relief valve, pressure setting the pocket must move zero point 0.3 centimeter from its fully closed position. Again, this is related to the this problem, and we'll see the data which you want to just take from this problem and then apply on this problem to find the initial compression of the spring of this pressure relief valve. So what we so this is again of course taken from this problem, but we are going to just consider it from the compression of the spring. So we need to find S. See, we need to find S. So area of the pocket is given taken from the problem A-45, K taken from A-45, and L additional. So this additional is taken because we need to just find the initial. Okay, so additional we take from here as it is. So additional compression is 0.3 centimeters. Again, now in this case, since we are not going to find CV, the capacity coefficient, so we are going to convert everything to what I used to. I used to do everything into base as a unit. Instead of centimeter square, I'm converting to meter square. K, of course, Newton per meter would be, of course, big, and the additional compression is 3 × 1 meters. So full pump flow is 1.4. Full pump flow or P cracking. So P full pump flow P cracking is 1.4 because they mentioned 40% greater, so it will be just multiplied by 1.4. I need to find S, the initial compression. So we know that again spring force equal to hydraulic force. In order for it to compress further to 0.3 centimeters. So K, of course, K is given as the value S. We need to go. This is the initial one. We need to find this one. Okay, P cracking. Of course, P cracking. Right now we don't know, and area of course we know. So we put this and we get the expression for P cracking. We simplify it. You will get this number as P cracking. Cracking is equal to this into S. Once done, because but just keep in mind we have to find S, not P. Okay, but we are going to use this to find S. Now after that, this is the initial cracking. Okay, this is but if we have the full pump flow, in that case you will again equate. In that case will be S, the initial compression, which you don't know, plus the additional compression which is given as 0.3, which is 3 times minus meter. P full pump we don't know, and A pocket of course we know this. So from here we get an expression of full pump flow as K S plus L additional over A pocket on this pocket. K value you put it, S you don't know, L this you know it, and then A pocket you also know it. So simplify you get this expression. Now we have two expressions. One expression is this one, another expression is this one. Now we are going to use this relation. This relation. We put the values here. Using this, we will find S. Because when you put this value, you just have only one unknown, which is S here and S here. I've shown you how to do all these steps to get S value. You move this one to the other side, multiply with this into S, and open this one. You have to do these two and move this to the other side, and then simplify to get S is equal to this over 2.2. Sorry, this over this because you want to find S, and then simplify, you get 7.5 plus or minus in meter, which is equal to 0.75 centimeters. So that's how we use this expression and the relation of the of P full pump flow or P cracking to find the value of the initial compression of the spring when it is installed. Now next is 8-60. Again disconnected with 8-58, which is of course in English units. So we will just leave the problem and convert everything into SI units, and then we want to simplify. But before that, we have to understand the circuit. Now circuit again is more or less same, but here the purpose is to raise or lower the weight instead of push or pull the weight in the horizontal direction, but it is in the vertical direction. So in that case, we have this reservoir or tank pump pushing the QP to a pressure relief valve just to have this pressure controlled within the prescribed limits. Then Q cylinder would be this the Q flow rate entering the blank side of the hydraulic cylinder with the pressure P1, which is of course very equal to the pressure setting of the pressure relief valve. Then at the exit, at the rod side, we have the P2. And then we have the needle valve to control the flow rate and also the speed of this descending or ascending piston at this time. So change the data and exercise 8-58 to metric units and solve parts A and B. So it means we just have to solve this problem in SI units. The system of figure A-52, which is this one, has a hydraulic cylinder with a suspended load W. Here you go. The cylinder piston and rod diameters are 2 and 1 inches respectively. The pressure relief valve setting is which is equal to P1 because the same pressure is sensed by this gauge as well as the same pressure is sensed at this end of the pressure relief valve. Determine pressure P2, which is this, for a constant cylinder speed if constant cylinder speed means again the A value of the acceleration will be 0. So this I'll make sure that if I give you something like that, I mention that whether it's a constant cylinder speed or speed with certain acceleration. Okay, if W is equal to 2000 pounds, okay, so we want this to be lower gradually. So we need to see if we have 2000 pounds, how much pressure P2 should be applied so that it can descend very slowly and without any damage in the way. And if there is no way W is 0, then what will be the pressure? So let's see. So diameter of the piston is given, diameter of the rod is given, the pressure relief valve P1 is given, P2 we don't know, we want to find out if the load is 2000 pounds, which is 8890 Newton, and if there is no weight or there is no force. So now we know that Newton's second law of motion can be applied here, summation F is equal to ma. Now we'll see how many forces we have. Number one, minus W, this is downwards, number one. Number two is minus P1 into A1. Minus P1 to A1, which is A piston. And then this is upward. So it is P2 into A piston minus A rod. See, P2 into A piston minus A rod. So we have everything. We have all the areas. We have W given for part A. See part A. We talk about part A. P1 you know, so we can find very easily the P2. But before that, we'll just find the areas of the piston and area of the rod. So we have all the areas. We put everything. We get P2 from. This is what is asked, that if you have a load of 2000 pounds, what will be 8890 Newton, what will be the pressure at this rod side of the other side? This is almost 12.715 megapascal. Then if we have no load, it's simple. If you have no load, there is no W. See, just the same expression, except that there is no W. W is used here. One and two expressions as it is here. Okay, then put the values and find P2, which is 6.87. So if you compare, it's almost double. 12.7 and 6.8, almost double. Pressure would be established to let the weight go slowly, or if you hold the weight still in the vertical direction. So I believe that finishes the chapter of hydraulic valves. We have seen some examples, and we have seen some problems that would give a very good idea about how to find CV, how to find the pressures at the rod side, or if I just give you the pressure at the rod side and ask you for the pressure at the blank side, means P1, you can find, or I should just say find the pressure relief valve setting. So in that case, you just put everything and find P1, which is equal to the pressure relief valve setting of the pressure setting of the pressure relief valve. So that's all. I mean, just I can give you something and find the other thing. It's much easier. Just the only thing for this types of problem is that you just have to apply the second law, Newton's second law of motion. That's it. And since um, it's mentioned constant velocity, so A will become zero and it will be zero. But if just in case I say, okay, with an acceleration of maybe 1.2 meters per second square, so just A value will be there, and of course mass can be found very easily from the weight by using G. You find mass, you have the acceleration, then you apply the same thing and you find the value. So these things are minor changes that can be very easily tackled in the exam with the same understanding. Okay. So any question until here? Any question that you want to ask related to any of the questions or any other thing that we discussed today? Yes, go ahead. Yes, any question? Okay, I think I'll go back and I will see if someone has any question. No, this is not question. This is thank you. I was asking about questions. Okay, if you have any, okay, no question. Anyways, that's good. So I've already uploaded this lecture. So with all the solution and all the details of these valves. So get ready for the quiz tomorrow. Prepare well. And if you have seen that already, it's very simple, small formulas. And of course, if I see there's something needs to be given to you from the formulas, I will give you at the end. So as soon as you get the quiz tomorrow at 7 p.m., just go and at the end and see the formulas that you might need. Of course, very simple formula I will not give, and I haven't added or include any simple formula that is very trivial. Okay, but if something like needs to be put, I have put already. Okay, so just prepare well, and inshallah tomorrow we'll have the quiz at 7, and I think I mentioned the room already, so just come to the room almost 15 minutes before 7 o'clock, so that as soon as everyone is ready, maybe we can start before 7, so that we finish early, we start early and we finish early. Okay, we don't have to wait until 7 p.m. to for everyone to come. Okay. No, 3 p.m. No, no way, because I have a commitment with Dr. Walid. So we are doing some other projects at 3 p.m. So it's not possible. It's not possible. And again, sometimes you are saying 3 p.m., but maybe some student will say, okay, I am busy, I have something. So 7 p.m. I checked, no conflict, no one has any issue. So this is only a matter of one day. So we'll do it inshallah quiz tomorrow, 7 p.m. Because it's only one time. It's not every day or every week. Okay, just you spare with me tomorrow. And as I mentioned earlier, please guys, I'm repeating, there is no makeup quiz because there is no time. So please make sure that if you feel that you will not be, you might be late. So come very early and stay there in the campus. Okay, so that you don't miss the quiz. Because I don't have time, I will not prepare any quiz, and I will not entertain any student afterwards. So make sure that you are there well before time. And if you are going here and there, just make sure that you at least 1 hour before you are there in the campus so that you don't miss it. Okay? I'll see you inshallah tomorrow 7 p.m. in the room which I mentioned already.
Doctor,
Yes.
since today class is online, can you make the submission of assignment until tomorrow?
Yes, yes, yeah, it's that's fine, that's fine, and because it was due today, but some students they submitted, but again, since there is a class online, and tomorrow, of course, you have to come. So in that case, if you are earlier in the campus for other classes, you can submit in my office. Otherwise, if you don't have any class other than this quiz, then just bring the assignment quiz time. Okay, don't forget. Okay, keep it with you right now. Okay, so that you
Okay.
don't miss. And yeah, because I need to start grading. I have so many things. Okay, Khalas, I'll see you tomorrow, inshallah, 7 p.m. and just see the room number. The
Inshallah.
last lecture. But what do you mean last lecture? I don't understand. Now we have to start the last chapter, which is the circuit design from Thursday. From Thursday on. But now we are just left with 3 lectures. One lecture on Thursday, and then 2 lectures on Sunday and Thursday again. Okay, and I'm very doubtful that that last Thursday lecture would be. I'm not sure, but so far they have mentioned that there will be no cancellation of classes, so we'll have regular lecture on Thursday next week, inshallah. So I want to just now spend these 3 lectures on these circuit design, inshallah. Okay, so we'll start inshallah from Thursday. So prepare well and practice yourself. Don't see the solution that I uploaded, but do yourself. I've already uploaded the practice problem, so just try to do as much as you can. Problems are simple, inshallah. I hope that all of you will get good marks. Okay, and good luck.
Doctor,
Yes.
just to make sure, what the lectures for the quiz? For the quiz
Okay,
material.
can okay. Let me hold on. Let me see the material for that. I have to see the material announcement. Yeah, the material says. Let me see. The material is a material. Ah, here. The material is chapter 6. Okay, material chapter 6 or chapter 6. Let's see what is chapter 6. Chapter 6 is, I believe, what is it? Is it hydraulic? Is it hydraulic cylinders? I believe it's hydraulic cylinders. Chapter 6.
Okay, thank you.
Oh, hold. Let me check. Let me check. I don't want anyone to be in confusion, so that I don't want to hear anything tomorrow. Yeah, chapter 6 is hydraulic cylinders. Okay, so just the only way to know how many lectures are there, just keep opening the lecture. Where you start the lecture for the hydraulic cylinders, that will be your first lecture to start with, and then you can continue until you see the hydraulic motors. So if I just can see, I believe, I don't know, but you have to just open and see. I'm just opening one lecture to see if the hydraulic cylinder. I'm opening chapter lecture 12, and that is no. So it is not the one. So maybe it's chapter 14 and 15, maybe 14 and 15. Let's see. It's opening. Yeah. Okay, so lecture 14, 15, which is mentioned lecture 14, 15 is the start of hydraulic cylinders. Okay, hydraulic cylinders and cushioning devices. Okay, uh,
So just
so it
these two
continues.
lectures.
Yeah, no. I'm just starting. So lecture 14, 15 is a one file. Okay, so let's see lecture 16. What is it? Let's see lecture 16. So 14, 15 is mentioned in one file. So it's one file. And lecture 16 is again, yeah, it's hydraulic cylinders. Okay. So 16 is all hydraulic cylinder with all the problems and solution with it. Okay, so 14, 15, 16. Let's see 17, 18. I think 17, 18 is hydraulic motors, I believe. Let's see. Okay. Okay. So this is hydraulic motors, right? So you have lectures 14, 15, and 16. So these are two files. In one presentation file is 14, 15 lectures, and 16 is a segment. So 14, 15, and 16.
Okay, thank you.
Okay. So these are the lectures and plus the practice problems of this chapter. Khalas?
Yes, thank you.
Okay, I'm going to stop the recording now. This recording will be available to you maybe in half an hour, 1 hour, but this you can of course use later on for the preparation of the final exam, inshallah. Okay, khalas. Inshallah, see you Thursday, and inshallah we'll try to start the last chapter number 2.
Doctor,
Okay. Yes.
I have a question about the quiz.
Mm-hmm. Go ahead.
What will be the problem solving or theory?
Of course, of course, always problem solving. You know this.
All
So
problem
always you
solving, the quiz.
no. If you know, I always put the theory as objective type. Okay, so theory will be there as objective type, which involves just conceptual and understanding. No, you don't have to memorize anything. So first question is the theory, which is covered with the help of objective type questions. Okay. Then after that you will have two more questions. So total three questions in 1 hour.
Okay.
Okay. Okay. Very good. Khalas.
So same
Inshallah, see
time as the
you.
announcement.
Yeah, same 7 p.m. 7 p.m. in that room. Yeah, just open, see which room is mentioned. I will be there, inshallah, before 7. And inshallah, we'll start. If everyone is there, we start before 7. Inshallah. Okay? Allah, inshallah.
Inshallah. Thank you, Doctor.
I'll see you all of you tomorrow, inshallah. Assalamu alaikum.
دكتور
Yes, any question? Yeah, anyone wants
Yes,
to ask
doctor.
something?
I
Yeah.
was saying that on Thursday, last Thursday,
Hmm.
you explained which lecture.
Last Thursday, I covered the directional control valves.
Direction control valves. Okay.
Yeah, because today we covered the pressure relief valves and the flow control valves. On Thursday, because it was one period, I covered only the directional control valves.
Okay, doctor. Thank you.
Okay, welcome. Okay, shall see you tomorrow afternoon, evening, sorry. Assalamu alaikum.